Thank you for the introduction. Again, my name is Kevin Stowe, and today I want to tell you about the return to the zombie gadgets. And this is work that I did along with Roman Rogalski, who is actually an undergraduate sophomore at the University of North Carolina at Chapel Hill. He actually did a lot of the low-level analysis and implementation work in this project. Also worked with Fabian Monros at UNC Chapel Hill, as well as Jan Warner at the Renaissance Computing Institute, which is co-located with UNC, as well as Hyung-Joon Koo and Michalis Polychronakis at Stony Brook University. So as I'm sure most of you guys are, see here. There we go. So as I'm sure most of you guys are already aware, over the past 10, 15 years, probably longer, there's been this back and forth between attacker and defender where they're constantly one-upping each other. And in the current snapshot of that battle, the most widely exploited applications are these really complex web browser applications and document reader applications, which all give the attacker these embedded scripting facilities to help the attacker create ever increasingly sophisticated attacks. Now, while widely deployed defenses already prevent an attacker from directly injecting their weaponized code into the process that they're exploiting, the attackers have taken a different strategy in the last 5 or so years of, instead of directly injecting their code, they're reusing bits and pieces of code that already exist in the application in what's called a code reuse strategy. And they're using the embedded scripting facilities to help them with this attack. So just quickly, the way I like to explain these code reuse attacks is with this newspaper article example. So the author of this article intended for us to read this article straight through and learn about daily blog tips. But instead, what we could do is circle various words and letters individually in this newspaper article and chain all of these selections together to form a new message, a message that the author didn't originally intend for us to learn. In this example, we've chained together letters that form the phrase return-oriented programming, and this is the name for the main technical tactic that attackers are using today to implement their code reuse attacks. And so in applications, it works much the same way as in that newspaper article example. So instead of paragraphs and words and letters, we have libraries and functions inside those libraries and instructions inside those functions. And short sequences of instructions followed by a return instruction are generally called gadgets. And so instead of the attacker highlighting and selecting various words and letters, the attacker provides as input to the program a series of gadget pointers and then redirects the program control flow to point to the beginning of this series of gadget pointers and takes control of the program flow such that when a function is returned from, the first return address provided by the attacker is popped off the stack, the short sequence of instructions in the gadget is executed, followed by a return, which has the effect of popping the next value off the stack the attacker provided and executing the second gadget. And this process can continue on for any number of gadgets until the attacker has accomplished whatever their intended malicious actions are. So fortunately, there's been a defense called address space layout randomization that's been around for quite some time that does a pretty good job of mitigating this code reuse strategy. The way this works is between 2 different runs of the same application, the program segments, so the stack, the heap, all the libraries, and the main program executable are essentially moved up and down in memory. So between 2 different runs of the same program, the memory layout is different. So this has the effect of the attacker is no longer able to know ahead of time where those gadgets are located at in memory. Unfortunately, there's a fairly simple attack that attackers have been using in the last 5 years or so called a memory disclosure attack that gets around this address space layout randomization. It essentially de-randomizes memory by using the memory disclosure to read the value of a function pointer off the heap. And then because the libraries themselves are moved around memory as a whole, and functions within those libraries are not randomized. If the attacker knows the address of a single function inside of a library, well, then they automatically know the addresses of all the other functions within that library, and hence all the other gadgets within all those functions. So to help with this problem, researchers have tried to create enhanced versions of address space layout randomizations. In general, this is called fine-grained ASLR. And the idea here is to not only move entire libraries up and down, but to also randomize the location of functions within those libraries and the basic blocks within those functions, and even instructions inside those basic blocks, and sometimes the registers used in those instructions. And there's been a whole bunch of different proposals for how to implement fine-grained ASLR over the years, but they all essentially mitigate this single memory disclosure attack that I described in the last slide. So at this point, we have application memory that's been totally randomized, but we can't forget that the attacker is launching their attack from a script that's supported in the application they're exploiting, so like a JavaScript in a web browser. So unfortunately, the attacker is not restricted to using this memory disclosure vulnerability a single time. They can actually repeatedly use this memory disclosure vulnerability, for example, by leaking an initial function pointer, all the code that function pointer points to, then scraping all the pointers off of that code page, and so on recursively until they've mapped out all of program memory and all the gadgets within the pages they've disclosed. So the attacker at runtime can find all the gadgets in memory, even when program memory has been finally randomized. Then within their script, they can take all those gadgets and automatically compile a payload composed of a sequence of gadget pointers to implement their malicious logic, and then redirect program control flow to point to that payload. So fortunately, over the last few years, there's been a whole slew of defenses designed to mitigate this sort of multiple memory disclosure exploit scenario. In general, they can be broken down into one of two different categories: defenses that attempt to prevent either the mapping of program memory or the disclosure of the actual data at that memory. So defenses that mitigate the step one, the read step. And then you have another set of defenses that attempt to mitigate the exploit at the execute step. So assuming the attacker is able to find the gadgets and build their payload, we want to stop the actual execution from happening. For example, with the last presentation, control flow integrity falls into this category. So I'm not going to go over all of the defenses that have been proposed in the last few years. There's way too many to do that in this talk. But what we became interested in is, of all the defenses that have been proposed out there, what defenses have been proposed that are actually binary compatible defenses that are usable right now, not just for toy applications, but for really complex applications like the Chrome web browser or Adobe Acrobat. Essentially, we wanted to find a mitigation that is binary compatible, so it doesn't require the use of any source code or compiler level instrumentation. It supports modules, so dynamically loaded libraries are supported. Requires no human intervention whatsoever, so it's mitigation that's completely transparent to the user. And to be usable, it really needs to have negligible overhead, so around 5% or less of runtime performance overhead. So when we looked at all the defenses that were out there, unfortunately, nothing met all of these requirements that we imposed. There's a lot of defenses out there that do a great job of enforcing really strong security policies, but they have the requirement of being embedded at the compiler level, requiring access to source code, or requiring debug information. So that's one direction a lot of defenses are taking. Now, on the other hand, you have defenses that are trying to be compatible with applications, like the last CFI defense. But the problem for us with this sort of defense is that in order to be binary compatible, without using source code, all of these defenses require a large amount of static program analysis. And we know that static program analysis is actually an undecidable problem. So what you'll see with a lot of these solutions is that they'll try to take a very, very conservative approach to analyzing the binaries to ensure that they're not instrumenting the program in a way that's gonna break compatibility at some point while you're running the program, while you're running just a benign process. And as a result of taking that conservative approach, you also have this trade-off of security in that in that you're going to miss certain points of instrumentation in the program, which can reduce the overall enforcement of the security policy you're trying to achieve. Then you also have defenses that are trying to implement something called execute-only memory. And the idea here is that in these multiple memory disclosure attacks, the attacker needs to be able to read process memory to find the gadgets. So the idea is that, well, okay, we have code code should not have data in it, so we should be able to mark every code region as non-readable, make it execute only. And so this works for some small applications, but if you look at larger applications, what you'll actually find is that data is very, very commonly mixed in with code inside the code section. So for example, you'll see function imports and exports embedded in the code section. You'll see local static function variables embedded right next to function code. You'll see switch jump tables also embedded, among a few other examples. So we sort of went down this path of trying to figure out a mitigation that we could build that sort of takes into account this problem of mixed code and data. And so we made the observation that in normal program operation, data in the code section is read, but it should never be executed after it is read, because it's either data or it's code in normal benign program execution. So the idea we had is maybe we can come up with some policy where if code section data is previously read, then we want to deny the subsequent execution of any bytes that were read. So at a really high-level view, here's the system that we implemented to enforce this policy. And we called it the no execute after read, or NEAR mitigation. And essentially, we divide memory into two different pieces. We have a read view of memory. So anytime a read access occurs, the application is presented with the data in the read view. And we have an execute view that's presented whenever an execution happens. So if we look at how this works when a multiple memory disclosure attack is occurring, the attacker has their script, they're using memory disclosure vulnerabilities to read all the code in the code section. This takes them to the read view because they're reading code sections. And so they would actually retrieve all the gadgets in the code section. This mitigation wouldn't stop that. But every time there's a read in the read view, we modify the execute view to replace whatever bytes were read with a 1-byte halt instruction. And so this has the effect of when the attacker comes back and tries to execute bytes that they had previously disclosed, the halt instruction is going to be executed, the program's going to crash, and that prevents their malicious actions from occurring. So we combined this no execute after read primitive with a fine-grained randomization scheme that works in a binary compatible way, and did some experiments, wrote a paper up, and then we saw that someone had actually just published this paper at CCS this last year with the exact same idea. So this was Heisenbyte thwarting memory disclosure attacks using destructive reads. We went back and forth with the authors of this paper a little bit, and they kindly informed us that our solution, NEAR, was just a bit too far. And it's true, we took a little too long getting it out the door. So that was that. But then we actually had a whole new perspective on this mitigation after seeing someone else's instantiation of it. We thought about this now from a completely adversarial point of view. And so now we changed our question to, does destructive code reads actually provide a viable defense for commodity applications? And thinking about it in this new way, we actually thought of 3 implicit assumptions that we had made in our work and the other guys had made in their work that was never thought of in designing the mitigation, that was never discussed in either of the papers. And then second, we found that we could actually break all of these implicit assumptions and actually completely undermine this new defense. And third, we think that one of these implicit assumptions that we broke relating to the ability to infer code in fine-grained ASLR schemes might actually be applicable to defeating other types of mitigations that sort of blindly combine fine-grained ASLR schemes with whatever their added mitigation is. So jumping into some of these implicit assumptions that we found. The first one is a code singularity assumption. Basically, we were asking the question, does duplicate code exist in memory? Because if duplicate code does exist in memory, what we could do is disclose and destroy the first copy of code, and then just adjust all of our gadget offsets to point to the second copy of the code. And then we would essentially be executing this second set of gadgets with the information we learned from the originally destroyed gadgets. And so we found that this is actually possible in practice. If you think about all of the browsers, they all have JavaScript engines in them, and I think all of the browsers these days have just-in-time compilation engines. So what we did is we generated a large random bit of JavaScript, and we evaluated it several times in a loop. And so this had the effect of forcing the JIT compilation engine to create multiple regions in memory, each with an exactly the same or a similar copy of this native JIT code that was compiled. Then we used our memory disclosure to follow a chain of pointers to arrive at the first JITted code region. We disclosed all of that code, which destroyed it in the process, but that's okay because we never executed that code again. Then we followed the second series of pointers to get to the second JITted code region, which is the same as the first one, adjusted our payload offsets, and executed the gadgets. So that was the first attack. The second question we asked, or the second implicit assumption, is code persistence. So we asked the question, does transient code exist in application memory over time? And the easiest way to think about this is with dynamically loaded libraries. For example, say at T0, we have this application with 3 libraries loaded. What we could do is use our memory disclosure to read and destroy the first library. Then, if we could somehow force unload this library, then somehow force reload the library, we would have a fresh copy of all the gadgets that we had previously disclosed. We would be able to execute these zombie gadgets. And so it turns out this was actually pretty easy to figure out how to do in practice. What we did is we had a little bit of JavaScript that called this create WebGL object function. And this was in Internet Explorer in this example. And this loaded the Direct3D library, which was needed to implement the WebGL functionality. Then we used our memory disclosure to read it all in, so it destroyed the entire library. And then we tried to force unload the library by setting our canvas object to null and reloading the page. So essentially, we were trying to get rid of all the references to this library. So we unloaded the library. No, actually, we crashed the program every time we tried this. And so actually what happened here is that when we set the canvas object to null, the destructor function was being executed every time, which we had previously disclosed and hence destroyed. So we had to add one extra step to this that we call responsible disclosure, where in an offline step, we trace through all the functions that are actually executed during normal benign program execution, and we whitelist all those so we don't disclose them. After we did that, we did our reload, and the library unloaded. Then we reloaded the library by creating another object, and we implemented our control flow hijacking attack from there. We're also able to do this with multiple browser process tabs because in recent security architectures for browsers, each tab is created in a new process. So it could actually disclose the entire memory of one process and then communicate all the gadgets to the second process and execute our gadgets from there. So the last implicit assumption we looked at was this code disassociation property. Basically, we looked at fine-grained randomization schemes that worked at a binary compatible level. And we asked the question, well, we asked several questions, but the one I want to cover in this talk is the question of, does a function prologue inform us anything about the function epilogue? So this is just one of a whole bunch of code transformations that are possible at the binary level. And this one's called the register preserving code reordering transformation. The idea here is on the left, we have a function, the instructions in a function. In the prologue of that function, we're saving a few registers. It's a pretty common operation. Then at the end of that function, we're restoring the value of those registers. So the transformation is just shuffling around the order that we save and restore registers in. But thinking about this in terms of destructive code reads, if we disclose only the first couple of push values, that actually tells us what the third push value is, because we know in this function that there's only 3 registers being stored. But on top of that, we know that at the end of the function, these registers have to be restored in reverse order that they were pushed. So by disclosing only a couple of instructions at the beginning of a function, we can infer all the instructions at the end and disclose the gadgets without actually reading them. So just to sum things up, we looked at 3 different attacks with 3 different implicit assumptions. The first attack using the JITted code regions, since we can generate as much JITted code as we want, destructive code reads provided no reduction in the percentage of gadgets. In the code persistence implicit assumption, since we had to only avoid the gadgets that were executed during normal program benign execution, that accounted for only about 30% of the total gadgets we could disclose. And then combining all of our code inference techniques, we're able to disclose still 90% of the gadgets that were originally available. So I'm just going to leave a few high-level takeaways up here for you. I want to encourage you all to read the paper, and I'll take any questions now. I'm getting signals.
So we have time for one very quick question, maybe.
Just quick. So yeah, thanks a lot for the very interesting talk. Do you think that there are use cases where we can use destructive code reads, or does it make sense to throw away this primitive and don't follow this path anymore?
I think there's probably things we can do to, I think if we just think about some of these assumptions, there's probably ways that we can implement additional defenses on top of it. I do have a few ideas for it. I don't think I'll disclose it in this whole room, but we can talk afterwards if you want.